Okay, so we continue our discussion on the tutorials. So this is the question for 1.22. A disk rotates steadily inside a disk-shaped container. So this is a disk here, and it's rotate. It might be a closed container here, means both side at the top here and also at the bottom here is contact with a fluid. And the oil has viscosity of mu. Assume linear velocity profile with no slip and neglect stress on the outer edge of the disk. So the stress on the outer edge means the stress at this area. So might be the disk is very thin, so we could neglect the area of this side. If the disk is thick, then you need to calculate two times. One with the idea of rotating this, because we have two moving area here, two moving surface here, which reflect the rotating disk, and also this area which reflect the rotating cylinder. And then I think we already discussed about this question. Find a formula for the torque required to drive the disk. So then, first thing that you need to understand in this situation is you need to know which surface is moving and what the form, the shape of the velocity distribution. For example, because we know that the disk here is rotating, then we could assume that we have a molecule here and also molecules stick at the top part, but the velocity distribution will shape like this. Okay, I think you could imagine this. And also another velocity distribution is actually shaped like this one. Okay, because the capability for you to understand this one will help you to determine which area that you need to calculate in the equation. So we have a three basic equation. Torque equal Fr, F equal tau A, and tau is equal to mu du dy. And you could start with dq, a small portion of torque that act on the surface. So you it start with dq equal df times r, and then you substitute the value of f here with you start to substitute the value of f here with tau a, and then you substitute the value of tau with tau mu du dy, and then you could solve it, integrating both sides, and you could get this equation. So we discussed this in a note, so I explain it a little bit shorter here. Okay, but and another thing that you need to understand is the value of torque that you have from you get from this equation. It is actually represent only the one side of the rotating disk. So if we have situation where both side is affected, so means you need to multiply it with 2, because we need to calculate the total torques to overcome the friction. And this is question for 1.23. So we refer to the equation of 1.86 from the textbook, that the coefficient of thermal expansion of a perfect gas is given by beta equal 1/T. Use the approximation to estimate beta, which is the coefficient of thermal expansion of ammonia gas NH3 at 20 degrees Celsius and 1 atm, and compare with the accepted value from a data reference. So this is just to show that actually in sometimes we always take reference from the table, and this is one of them. So we could calculate actually that data by using an equation, but sometimes we just take from the table. For example, for a perfect gas, so it is assumed that beta is equal 1 over T. But for liquid, so the thermal expansion is less than 1 over T, and the imperfect gas is beta is greater than 1 over T. So it's written in the textbooks. And then the idea is we are using the idea of this one. So we have beta is equal negative 1 over rho over del T, and it is for pressure here. So and then it is of perfect gas. So so we replace this one with we bring out the dt here, the thermal, because in this situation we are discussing about a 20 degrees Celsius. So and then we could replace the rho here with P over RT, and then we could substitute, and finally we could cancel the value of rho here, and finally we have 1 over T. So and then for ammonia 20 degrees Celsius, so it is equal to 293 Kelvin, which is equal to 1 atm. So and then the beta here, if we calculate, it is equal to 0.00341 Kelvin negative 1. So and from table we could also say that with this and from table we could get that beta is around 0.00245 Kelvin. So the way is if you have the beta here, and then if we go for a 20 degrees Celsius, so and then we could get it is around 0.00245. So there is a little bit increment here, or the value is not the same, because in table, so they will validate with the experimental works, and then they will have the very optimal numbers for that situation. So and then for 1.24, so we have the rotating cylinder here. This question is the rotating cylinder viscometer shares the fluid in a narrow clearance delta R. So we have a delta R here. Assuming a linear velocity distribution in the gaps, if the driving torque M is measured, find an expression for mu by neglecting the bottom friction and including the bottom friction. So for the A here, so they ask you to calculate the value of mu here by neglecting the bottom friction. So when the question asks you to neglect the bottom friction here, means you are calculating only by the idea of rotating cylinder. And if you need to include the bottom friction here, you need to add, means the total torque here is actually the torque that came from the wall here, mean the rotating cylinder, plus the torque that came from the rotating disc at the bottom here. After you sum all of them, both of them, then you can get the value of mu. So in this question, they ask you to calculate the value of mu, which is the dynamic viscosity, but actually it is okay for you to start the calculation with the m, with the torque. So I just skip the solution for this one. So you could refer from the notes, previous note when in this subtopic. So for if the rotating cylinder only, means we are neglecting the bottom friction. So the torque here it can be written as this one. Okay, might be H here is the okay. So if you rearrange the equation here, you want to show up the value of mu here, you could get that mu is equal of this one. And then if you accounting the rotating cylinder and plus the rotating disc, the rotating disc here is actually reflect the bottom part of the rotating cylinder. And what you need to do is you need to add the torque from the cylinder and the torque from the disc. So it is okay for you just to use this, just to use the equation for the top here. So without to derive it, because the question asks you to just to apply the equation. So you may have use both of this equation, and finally you will get the mu here is equal of this equation. So this is the example on how the dynamic viscosity measured in rotating device. So, but manufacturer will calibrate the machine with the a few oil or liquid, and then they will create a graph, and then they will give some kind of coding, a program there to make sure that we could get the value of dynamic viscosity when the machine accept when the machine supply a certain value on top. And this is 1.25. We consider that 1 meter cube of a fluid at 20 degrees Celsius and 1 atmospheric pressure. So for an isothermal process, calculate the final density and the energy in joules required to compress the fluid until the pressure is 10 atmospheric pressure, 10 atm, for air and water. Discuss the difference in the result. So this property can be found in our textbooks. So it is table A1. So we have the water atmospheric pressure here. So the idea is it's depend on the bulk modulus. So and then we could say that to make sure it can be deformed, so the value of k is greater than 0. So we have from the textbook we could use k is equal minus v dp dv, where the p is the pressure, v is the volume, and dp dv devotes the derivative pressure with the respect of volume. So and then at the same time, if we substitute the value of mass, and then we can cancel it everything, so we could get it is equal rho dp over d rho. So you know the volume is rho is equal mass mass over volume. So and then okay, and you know that the rho is the density, and dp d rho denotes the derivative of pressure with respect to density, and the inverse of the bulk modulus give a substance compressibility. So other equation describe this the material response to other kind of stress. The shear modulus describe the response to shear, and Young modulus describe the response to linear stress. For fluid, only the bulk modulus is meaningful. For an isotropic solid such as wood or paper, these three moduli do not contain enough information to describe its behavior, and one must use the full generalized Hooke's law. Okay, so we have this one. So we have work, so which is the integral of pressure with volume here. So and then we could substitute P volume here is actually equal to MRT. So usually we remember this one as PV MRT. So we just change, I just change the symbol here to make sure that it is not looks like a velocity. So this is the equation for volume, and then if we substitute all the idea here, okay, because we have the condition number 1 and condition number 2 before and after. So because the question asks us to compress at to the certain value. So for air, for example, we have a P1 V1 ln P2 over P1. So we substitute the atmospheric pressure for air, and then we have the volume, let's say as 1 meter cube, and then we have the ln for 10 joules here. So our pressure is 10 atmospheric pressure. So it is equal divided by 1. So the ratio, and then we get 233,000 joules. However, Okay. So, however, for this is for water, I think. Finally, okay. For bulk modulus K, it is a measure on how resistant to compressibility that substance is. So we have K here. So for water, which is 20 degrees Celsius and 1 atm, the value from the table is around 2.23 times 10 by the power of 9 Pascal. So we substitute into the equation, and we finally can get the delta V here. The volume is minus 0.0041 meter cube. dP is the pressure difference. From the question, pressure of water was changed from 1 atm to 10 atm, so that the pressure difference is 9 atm. So this value need to multiply with 101 kilopascal to get the value of pressure in Pascal. So the work is, if we calculate the work, it is equal to 229 joules, and the average the average pressure used to compress that one is actually, we can assume it is equal to 5.5 atm, which is atm is around 101 kilopascal. So the value of work is around 229 joules here. So we assume that it is too small, so means that the water cannot be compressed. So the idea here is, for example, you have a machine there, you try to compress a water. So, and then when you compress it, so you find that your machine is actually give you just a very small amount of work. So it is not mean that by 229 joule you could compress water with until 10 atm, but it showed that it's you just think like you have a machine and your machine is start to press, but until it reached 229 joule, so your machine stop. So means that you need actually a lot, might be greater energy to compress water until 10 atm. So, but in reality, we assume that we cannot compress water because it is totally incompressible fluid. So, and then for question 1.26, for example, we have two equal layers of two immiscible fluid are being sheared between a moving and a fixed plate. So assuming linear velocity profile, find an expression for the interface velocity u as a function of v, mu1 and mu2. So the idea is, okay, we have two plates here. One is fixed and one is moving by this velocity, capital V. And then you know that we have two different fluid here, mu1 and mu2. And the question asks us to find what is the value of u at the center of these two plates. Okay. We could calculate the value of shear stress. So the main idea is tau is equal mu du dy. And then as I mentioned previously in early of our class, so the idea of tau equal mu du dy is specifically for one fluid. So if we have a two type of fluid here, so we need to use two types of equation. So for example, for fluid number 1, so we show as tau 1, so we could write as mu 1 v minus u over h over 2, and tau 2 is u minus 0 h over 2. So here I think you could understand that for the top situation here, so because the velocity difference is v minus u, so we use the du as v minus u, and but the bottom situation here, so the difference is u minus 0. But because at this bottom plate here, molecule will stick together very hard here, and it will create no slip condition. So that's why the velocity at this in this location is equal to 0. So and then we equal the tau here. So we have this term. So and then we could say that U is equal to mu1 over mu1 plus mu2 V. Okay, so and then this is about the rotating cylinder. So use the Inviscid flow solution of flow past a cylinder, equation 1.3. So find a location and value of the maximum fluid acceleration along the cylinder surface. Is your result valid for gas and liquid? And then we need to apply formula for A max, acceleration max, to air flow at 10 meter per second past a cylinder of diameter 1 centimeter and express your result as a ratio compared to the acceleration of gravity. Discard what your result implies about the ability of fluid to withstand acceleration. So this idea is actually comes from when we study about the ideal flow. We have linear source, sink, and vortex, and then we merge the sink and the source, we get the doublet, and then we merge, we combine a doublet with linear, then we get the around flow cylinder. And if we add vortex inside the stream function, means we have doublet plus linear plus vortex, so it will show about the flow around rotating cylinder. So I hope you still remember about that. So and then by using the Cauchy-Riemann equation, we could derive UR and also U theta from the stream function of flow around cylinder. And then when we derive that one, we could get that UR is equal U1 minus R square over R square cos theta, and U theta is equal of this one. So because the cylinder is a solid object, so means the R here, the radius is fixed, so we substitute the value of R into the equation of velocity. We have two equations for velocity, and we found that UR here is equal to 0. So it's mean that the molecule of fluid will travel on the surface of cylinder only. So and then for U theta, if we substitute the value of small r with equal of R here, so we'll get it is equal to minus 2U sine theta. So the minus here is can be ignored because it's just to show the direction, which is it is counterclockwise. Okay, so in some textbook, I think in our textbook here is not our viscous fluid flow textbook, it ignore the value of minus. But some textbook, another textbook, they will strictly use the minus sign here. Okay, so from this equation, what we could say is actually we could say that we could determine the maximum value of velocity. So it is occur when the theta here is equal of pi over 2. Okay, so and then this is the idea of acceleration. So this the A is actual U times du over dy. So this is the common acceleration function for ideal flow. So as you know, the common equation for acceleration is U2 minus U1 over t. So and then means that we differentiate the value of du dy. So we substitute all the value here, and finally we'll have all of this. So and then we could say that the A max will occur at pi over 4, which is 45 degree. So and then we assume that all this result is valid for all fluid, gases, and liquid. For all fluid, gases, and liquid in the Inviscid in the Inviscid approximation. So it means that by this one is we just assume that the effect of viscosity is actually cannot be account, because if the effect of viscosity is take into account, so for sure they will have a condition, they will have no slip condition, with will create the velocity profile with in certain will stop the velocity on the surface of cylinder, and then they will create boundary layer, they will create a velocity profile on the surface. So that will interrupt or will ruin the equation. So normally this one is actually used for the ideal condition, means in Inviscid approximation, mean in Inviscid flow. Okay, so if the U is equal to 10 meter per second and R is equal 0.005 meters, so we substitute the value here. So the A max to is 40,000 meter 40,000 meter per second square. And if we compare to gravity, so we divide by 9.81, so it is 4,000 G here. So it is mean that this fluid could resist pressure for more than 4,000 G.